Okay, so we get started on our next speaker, Dr. Takeo Kanade. So Takeo Kanade was the director of Robotics Institute when NREC was founded. So he helped us a lot in the founding of the center. He is also the founding chairman of the Robotics Ph.D. program at CMU, which I benefit from. I'm in that first class of PhD program. Takeo Kanade professional honor include the Bower Award from Benjamin Franklin Institute, the ACM Helen W Award. Okay. He also recently won the prestigious 2016 Kyoto Prize for Advanced Technology for his pioneering contribution in computer vision.
All right. This is the talk title that I sent in. And then Herman said, oh, Raj is going to talk about it. Don't talk. So, okay, so I have to change. This is a picture, by the way, the official opening day. And you see young Takeo Kanade was sitting there. So I don't talk about those things, but a more technical thing. So I may, technical and non-technical, I may sort of bore you if that happens. I'm sorry. So I think as one of the, probably the longest a person who works on computer vision for longest period. I think I've been working vision for more than, well, if I include my PhD days, in 50 years now. And this is the end of my PhD, face recognition, 43 years ago. And can you imagine? It was coded in assembler language. Run on a computer which has only 20 kilobyte, not megabyte, kilobytes. And cycle time is 10 microsecond, cycle time. By the way, I always tell the students that compared to this machine, students have at least 10 to 3 advantage minimum, probably 10 to 6 to 9 advantage in terms of memory. 10 to 3 advantage in terms of cycle time, 10 to 3 minimum advantage of external disk. So if you multiply all of them, you should have 10 to 9 advantage, which means that what I could do in 1 year, you should have done it with 1 to 10/9 of year, which is about 30 milliseconds. You know, technology. But anyway, at that time, by the way, at that time, if you apply your program to 1 image, you could write a paper, 1 image, if it's successful. Because digital image was so rare that you could apply only 1 image. And by definition, your program works, because you can change parameters exactly so that it works. And if you experiment with 10 images, we used to write a paper boasting, with a large-scale experiment. I processed 10 images. Now, my professor was very far-seeing professor, and he collected 1,000 images at that time. And so at that time, this was one of the rare computer vision program which could process probably more than 10 images. Or order of 10. Kelly had, what, 50 or so images? Stanford, Raj Reddy's student wrote a face recognition program around about the same time. Anyway, that was then. Now, of course, since then, I, with my students, did some face detection work in 90s, 2 of which actually, all of these 2 actually got the Longet-Higgins Award, which is the award that Vision Conference gives 10 years after you publish, saying that this is the most influential paper in the last 10 years after looking back. And these two students actually got awards. So I'm fairly proud of it. And then today we can do this level of performance of detection and alignment and so forth. But actually today, if you look at today's technology, face recognition today is by deep learning, most of them, based programs now exceeds a human performance. By the way, isn't it funny? If you remove the face itself, which that one, which is inverse mask, still people can recognize famous people. So it's not face recognition, obviously. It's so funny. Probably deep learning, that kind of program is using other than just this part, which most of the traditional face recognition program typically use. Now, this is scene segmentation program 40 years ago, 1975, with my student Ota. We are very proud of it, by the way. Picture and initial segmentation, which today you may call superpixel, and a very large network of knowledge, and run on it and segmented that image to tree part, building part, sky part, and so forth. Again, on that computer, 20 kilobytes, 10 micro machine, 10 microsecond machine, on which we wrote a Lisp program on Fortran. And all of these things were represented in that Lisp, which was written on Fortran, which runs on that small machine. Now, today, of course, Marshall and company can do this kind of thing, which actually not only segments, but also do a lot more reasoning about distance and that type of geometrical and other reasoning. And when it comes to object classification and recognition, this is a competition that ImageNet, which is a large network, about 1,000 object kind, and apparently the performance now about the same or exceeds a little bit human performance. And for what I call multi-camera vision, use a lot of cameras, not just one or two, but many. Back in 90, we started with a 5 camera stereo, which consumed, by the way, 5 kilowatts. If you turn on the machine, it's hot, really. And it has about this size board, 5 of them. That include 11 by 11 convolution chip, which is each of which is about this size, $500. So that was interesting. And by the way, when I wrote this paper, it was rejected. Can you guess the reason? It actually says, really, this is not a fake story. It says that this machine, which uses unnecessarily large number of cameras for stereo, can be built only by people like Kanade, who has enough money. But nobody would use such expensive machine. That was the review of this paper that came back first. And it took some time to convince to publish this paper. Indeed, I don't think we published this in any significant publications, except in Japan, probably, I think. So that's interesting how expert understanding will change. And this is a 51 camera dome system that we built 1995. Around that time, Peter was actually struggling with this a lot. And it was fun. It had 50, because at that time, digitizer was expensive. It's not just like just connect the USB. You have to actually have a digitizer board, which is about $8,000. So you can't prepare 40 of them. Therefore, you prepare only one. And then record all of the video in analog videotapes. And then remove one and put it to the digitizer like this 51 times. Student's job. And all of the video is time coded so that we know which frame corresponds to which between across the videotape. It was a lot of work. And so this kind of, we call it 4D model and synthetic cord. So I was very, looking back, it was an amazing job, thing we could do back in 1995, 20 years ago. And then of course I had a fun to work with CBS 15 years ago to do EyeVision, matrix-like video replay used in Super Bowl 2001. The 33 cameras were camera and robotic pan tilt device was put surrounding the stadium, 33 of them. All the hardware cost alone was about $2.4 million. It was an interesting system, and this is how. Just 1 second.
Now, during.
Is there sound here? No, maybe that's okay. Oops.
Get sound on yours.
Now, during today's coverage of Super Bowl 35, CBS Sports will introduce a new technology called EyeVision. It provides panoramic coverage similar to the special effects in the hit movie The Matrix.
So this is what I call my moment of fame.
Here at the Super Bowl, 30 robotic cameras have been mounted on the scoreboard and all along the upper deck at intervals of 7 degrees. Each camera feeds into one of the 30 specially designed
This is the video recorded
The images are then
at that time, that big.
to instantaneously
Today is
show
probably
any
about this
spot on the
size.
playing field from all angles within the camera's 220-degree range. Professor Takeo Kanade of Carnegie Mellon was designing the software that blends 30 cameras into one dynamic panorama.
This is a gigantic robotic system. You have to have perfect idea of the direction, position of the cameras, and the relationship of the amount of zoom, amount of focus to the command that you give from the computer. And that is one of the hardest jobs.
This is inside a control station.
Here it is. This is an example
trailer.
during the warm-ups, taken just a moment ago. The pass from Banks to Davis, and look at the way it can whip around. We're all looking forward to it. By the way, it can be used in instant replay situations in the case of a challenge.
We will talk from time to time tonight about EyeVision. If you're wondering what it is, this is what it looks like.
You got a pass rush, quarterback, he drops back. Look, he sees a big lane. Look at that big lane, so he steps up into it. What always makes it easy for a quarterback is to have a clean line of sight. Watch Trent Dilfer, nice look off, looks to his left, and nobody in front of him. Look at that nice lane. He can see the receiver down the field, and what a throw.
So it was really pain and fun. It was stressful development for 6 months. And by the way, Can you imagine that the 25-second appearance on the Super Bowl program is part of contract? So contract explicitly says, Article 6, Professor Takeo Kanade must appear with his name and title clearly shown. You see my name and title for 25 seconds during the broadcast of Super Bowl. That was a contract. So that was what I usually call my biggest moment of fame.
50 million people saw you.
Yes. Today, yes, our Sheikh built 1,000, currently 480 camera system. It actually generates 20 terabytes of data in 1 minute. It's interesting. Raj talked about autonomous driving. 30 years ago, we started what Red built Terrigator, and then NAVLAB 1 and NAVLAB 5, 1 to 5, and 5 went to California, No Hands Across America campaign, 3,000 miles, 98% driven by program. And this is also a fun picture. I don't know whether you can see. This is Jay Leno. This is me, Dean Pomelo, and Todd Yoakum. The reason that we showed this to show this NAVLAB to Jay Leno uses a news article for joke, and indeed he used this. It says, thanks to Carnegie Mellon University researchers, now for the first time in the world, you can take your hands off while driving and read newspaper or do makeup and so forth. And he said, how come this is the world first? People have been doing this forever in Los Angeles, and that was his joke. And so we thought we should show this to him. And then, of course, Red did one urban challenge, 2007, and today, as you see, the autonomous driverless car is real, Google, Tesla, and so forth. To the point, actually, it begins to have accident. I think the fact that it, well, I should not be too jokey about it, but to the point that it actually does have causes an accident, means that it actually has some trust. Unfortunately, that was not perfect. Yeah. So that's great. That's how it. So in that sense, I think vision has been good and bad. I think to a certain extent, it did, as you see, advance quite a bit during my personal trajectory as a researcher for at least 45 years since my PhD day, and I'm very lucky to have involved many aspects of that, more than what I showed here, color, and then structure, structure for motion, SLAM, and all those things. And good and bad thing is I'm proud that I started some of them and pretty good at that time, but now it seems that all of them have been exceeded by, surpassed by current programs. I wish I have some program which works better than. Now, helicopter, by the way, Omid's helicopter is probably still par with most drone programs that I see. And it's unfortunate that he didn't write a paper, but that was pretty good. Now, so after all, what is vision? Vision is basically, there's a seen three-dimensional world, and we have a device called camera, and that takes data, what we call image. And vision is nothing but going back this process. Given image or images, create some kind of description or understanding of the original scene. So that's vision, okay? And if you think that way, actually computer vision was one of the earliest problems in artificial intelligence back in even 50s. Even when, if you read Toward Artificial Intelligence, Marvin Minsky's paper, he has all kinds of topics and a list of challenges and even methods on vision. Now, the original game plan was kind of followed by the first work, Roberts. Roberts actually he's an interesting person. He got a Ph.D. and then right after he finished it, he went to DARPA, right? And then just quit doing vision and began to do all other computer networking and later program and so forth. Anyway, so the original plan followed exactly what Robert did, starting with the original image and going upward from a lower level of features, in his case line, and features and segmentation, and then somehow cross the boundary between image and scene. This is an important boundary between 2D and 3D, and then shape and relationship, functions, object, and so forth. That was the plan that people thought would work. So from signal to symbol, all kinds of classification, segmentation, recovery, detection process algorithms were invented and worked. And then AI-oriented people said, okay, the most important thing is knowledge representation. Raj used to say that. And then write, model of the scene world, and then reasoning program, and all kinds of it. Raj presented a blackboard model, and vision people also try to use it, and so forth. Now, it turns out computer vision is so difficult. Was successful at almost none, to a certain extent. And as Minsky's episode is a famous one, which when I asked him, he said that was not true. But what is often said is that he thought the vision is so simple that he gave the task to students as a summer homework. And okay, you're smart enough, you finish it during the summer. But it took, even after he passed, I don't think we have solved yet, 50 years or 60 years now. Now, why? Because fundamental difficulty exists. Because we're talking going from 2D back to 3D, which is basically impossible theoretically, because we're talking the recovery of degenerate information. We lost depth, so there's no way to go back uniquely. It's obvious, but somehow human thought we could, and we obviously do reasonably well, but to a certain extent, theoretically speaking, that's an accident, because you cannot do, right? You cannot, once you multiply 0, there's no way to recover the original number. No way. So that is what vision is asked. And obviously, the signal-wise too. The pixel value, for example, is the combination of many, many facts. It doesn't represent the color or brightness of the object. It is a combination of that with lighting, atmospheric effects, and all kinds of things. So, and also The most difficult AI-ish problem is knowledge or concept. And I like this slide. If you look at this slide, and if I ask, what is this? You say, car, yeah? Well, obviously, so here, picture over there. Now, if you remove all of, and then if I ask, oh, what is this car? And then why nothing but square, rectangular shape car? And then you say, well, because it is on a road. Context, it's called. Then if you remove, indeed, all of the context, it doesn't look like a car. So context is working. And then, okay, now I understood. Now, why then is this a road? And the people say, well, because there's a car on it. Well, that's exactly what the AI tried to solve it. And didn't work. This cyclic phenomena. So what happened is actually this part going back up is obviously one to many, and extremely noisy mapping. By definition, it's one to many. Okay, and in the meantime, the upper hand, the knowledge representation, expected that, and then thing like road. When you see 4 legs, it is likely a chair, or that's a knowledge that vision people should use. And I also used to debate with AI people and say, if you give me a program which can detect 4 legs reliably, we can switch the job and I can write a code, fairly good code, from which I can recognize a chair. So this is, I call signal and symbol mismatch. So we didn't talk between AI and computer vision type. Good. So another thing is like a knowledge. Knowledge was hand-coded. And indeed, my OTA's program is like this. You say, okay, when we see square, when you see one, rectangular shape, look for other rectangular shape if they are aligned. If they are likely window. That's knowledge that my OTA thought. And I said, great knowledge. And okay, so how likely is that? And then he said, yeah, I think it's about 0.95. Okay, put that number. And there's somewhere that number. So every time it says, okay, if you see a straight line between gray or blue region and gray region, it's likely the top of the building. How often? I think it's 0.7. Okay, 0.7. That's what we wrote. Seriously. And even after we wrote, actually run this code and check all the possible combinations, not all, but many possible combinations of the superpixel, so that they actually form, check if they actually form a square and line up and so forth. The combinatorics is extreme. And at that time, of course, not only we have a computation power, but also we don't have any search method like, generic algorithm, random search, nothing. So it's simply either depth first or, width first. So naturally, it exploded. And it didn't go any deeper than probably 2 level, our program. So you see, it's obviously a failure. So in that sense, computer vision and AI had a clash between signal and symbol mismatch. And as a result, I think computer vision people took their own engineering path for a large part and worked on individual process very hard. And I think we made a pretty good job in terms of how to analyze color, how to analyze shadow, how to analyze shape, how to analyze a sequence of image from which obtain 3D, like a SLAM and so forth. However, when I look now today, I think recent results, especially by deep learning, may give a chance to bring computer vision AI back together. And I think this is a topic I like to talk a little bit. So if we look at deep learning from the viewpoint I just explained, to me it is amazing, because I've never thought about it for a long time, that from signal to a particular thing, object or name or segmentation and so forth, which you may call perceptual process, relatively simple, single purpose perceptual process, can be actually learned without human designing features, how to assemble them into a larger features or complex features, how to use them, map them into a particular decision. And that can be learned if you have enough learning samples. And I think it's an amazing discovery. And indeed it worked. And as I showed, it worked obviously to the level that some of the task performance is equivalent or even better than human. This kind of, probably not this one, but some of these things are already equal or better than human. Okay, so, and then amazing part is this perceptual process can be even go beyond image or vision to the level of robotics, say, action, like control. In the case of driving, instead of actually producing explicit representation of where the road is and so forth, you can actually drive drone or car, even though apparently this video is interesting. In order to learn this, you have to do a very dangerous thing. Because actually you have to, I don't know whether have to, you need to create a situation where program has to learn, which means that you have to, the program has to be exposed. No, I don't know has to, but it apparently did or was exposed to non-regular situation, which means very dangerous situation, about to hit something or even hit something or outside of the road and so forth. By the way, when I look back, Dean Pomelo, when he wrote the Ph.D. thesis with the NAVLAB, he called neural net, Alvin. He actually solved that problem very cleverly by artificially shifting the image of the road, so that even though you are actually on the road, the picture is given such as this way. And then program learns to go this way. Yeah? That's what it did, and a very clever way of producing learning samples at that time. He did it back in 1990s, and so good ideas also always come out. So my question is, what now then? I think, and I hope, vision is not, and it is indeed more than a collection of perceptual tasks. It is total understanding, or it should be, of the scene and situation, and capable of reasoning about it. Very simple case, simple example that I, somewhat artificial example that I often use, this. When I ask, okay, which side of this is the back side of the rear side of the car? Now, visually, there's no difference. So I said, well, I understand it. Why? Because there's a signboard which is written in Japanese. So I said, okay, this must be in Japan. Now I know the traffic rule in Japan, which says you drive left-hand side. Therefore, this car, this side must be rear side. Okay? Now, things like that I'm not sure if it's a useful reasoning, but what I try to say is reasoning actually goes all the way from pixel, like a recognition of a signboard and then Japanese and so forth. And then reasoning goes up there and then come back about understanding of the picture. Yeah? So that type of things, I think, should somehow be included eventually into the computer vision program. Otherwise, we don't have a program that has a common sense, being able to infer things, explain the answer that it generates, not just say this must be a good one, but explain why. And that is known to be, by the way, very important, Raj pointed out, like application of, say, Watson to various medical situations. You can't simply say this is the best treatment. You have to explain, program has to explain, otherwise people don't take it, even medical doctors. So vision must be same thing. You may call, we call it self-aware program. And also, I call it explicit understanding. In other words, it says, this is the answer. I think this is, the road is this and this. But if it is wrong, this could be wrong this way. Or self-aware, how much I'm actually wrong. By the way, those percentage of the reliable certainty that program tend to generate, I'm not sure if that's self-awareness, because it does not know how good that is. Okay? How good that is actually determined by the people who receive that answer. That's not good enough. The program has to tell, yeah? Which I call the real, genuine self-awareness. So I don't know the correct answer, but from the way it came, probably some kind of a hybrid neural net way of deep learning, neural net way of representing this low-level representation by weights and vector weights and so forth, which is implicit. And also symbolic representation for a higher level knowledge representation and reasoning, which hopefully will create and overcome that signal to symbol mismatch, and it may generate continuum of that, and then of that relationship. Then it should do a good job. The second thing I think we should, I like to see in myself, is to go beyond. Now that I think there's a chance that we can be as good as human, not yet, but can be, we should look at, go beyond human can do. Now, there's an easy way to go, easy way. And so I like the easy way, so I only show two ways to go. One, I think new sensors. It's obvious that the human doesn't have enough good sensors compared to other animals, or even artificial system. We don't have SAR, synthetic aperture radar. If we do, we can do probably a lot better job in many tasks. If we can see 200, 300, 500 away and exactly measure distance and so forth, probably we can do a lot better. Now, if you think that way, actually animals have, some of them have extremely good sensors. I think they wish they also have a good brain too. So if we actually have a good brain and good sensor, we should be able to do a lot better job. And in that regard, probably you know this work, but I'm very excited about this work that Srinivas does, and I had some work with him, which is the Smart Headlight, yeah? Which basically says, when you drive at night, the raindrops will bother you because they reflect the headlight's light. So how to avoid that? Solution is very simple. Simply, when you see them, turn off the beam ray which will hit the raindrops, and so that the rays won't hit the raindrops, and then the light won't reflect it back, and therefore the driver won't see raindrops. And isn't that a trivial idea? And indeed, solution is trivial. Indeed, the trivial. If you look at the short exposure picture, raindrops indeed are drops and fairly easy to detect. And if you devise a device in such a way that camera and projector, basically that device, are co-located, coaxial, then visual ray and shooting ray is the same. Therefore, independent of the distance, if you see the ray in the picture domain in this direction, the same ray of projector should be turned off. Now, since it takes a little bit, if you can process it instantaneously, that works. Since it takes a little bit, you have to be a little clever, so that if you see the raindrops here, a little bit lower than that will be very dangerous because the raindrops will come here. Above, very safe. This side, well, wind may bring the raindrops this way, so pretty dangerous. Therefore, you have some kind of a probabilistic distribution of how the probability that your ray will shoot. So you should control the ray inverse proportionally to that probability. Then you can lower the probability or percentage of the ray that will shoot the raindrops. Because, by the way, the goal is throughput, not make them zero. If the goal is to make the probability zero, the best solution is turn off the headlight. Yeah? Then it'll never hit. But that's not good enough. Yeah? You have to turn on. And so this is, you modify that projector, basically, so that it actually run at much higher rate, speed, about 2,000 frames per second instead of 60. And then put the camera coaxially and then put it on a truck, and then look at it, and then you don't see rain, and you don't see snow. Okay? Now, the more realistic application today is probably the headlight, which will be for you, for the driver, high beam all the time, for the incoming car driver, low beam all the time. So by the method where the headlight will be always shining a lot of light, but turn off only the beam which will correspond to the eyeball of the incoming driver. Then for him, this headlight is not up beam. So that's the idea, and indeed that works. Oops. Okay, so I don't have enough time. Like this. This is, you don't see, it's, you know, the glare, but for you, it's always high beam. And as soon as you see that, you can do a lot of things. When today, computer actually can detect pedestrian, bicycle probably better than human driver, especially at night. Therefore, once it's detected, you can actually send more lights toward it. Then the human driver actually has a better view. Okay? This is very different from seeing the picture of better picture on the display. Okay? The cell phone, and look at this, and then it shows the name of the person. It's often called, or do this, and then a lot of display, augmented reality. I usually say that's not augmented reality. That is augmented display of reality. Because if you remove the display, the reality is not augmented. See? Whereas this is, reality is augmented because your eye actually sees it. Yeah. So I think that's interesting. And finally, I think one of the go beyond vision should actually take advantage of computing power that will surpass humans. And this will come, obviously. Obviously. I think today, the ratio is about 10 to 4 to 10 to 5, 10 to 6 maximum. Within a few, I don't know few, too optimistic, but definitely 10 years, I think the raw sheer computation power will surpass humans. If we combine, if we take advantage of that, all these technologies being developed, then why not? We see everywhere computer vision program systems which surpass human or any animals. And then I think we can do a lot of interesting things happen. So I think my conclusion is computer vision has a lot to do and long way to go. And by the way, Raj said he gave the job of computer vision to me. That's good, but I'm very careful not to solve all of them so that my job is secure. And let's see, when I retire or finish, maybe then everything is solved. You don't have any more job security. Thank you very much. I talked a lot, yes. Sorry about that.
So, by the way, we do have that Smart Headlight demonstration in the other highway. So now it's actually inside the car.
Good,
Yeah.
okay.
So, probably you have time for one question.
So all the things that you listed, which one are you doing now?
I actually,
Career, no?
now you know that I'm in Japan, and I have students in Japan, and a couple of students, and one of the projects I'm interested in different domain than natural domain. The reason is there are lots of bio or nanotechnology area. Actually, they are vision problem. Interesting, you may call camera, but not the visual camera, even though input for human scientists, they are image, because human only can interpret images. But computer doesn't need to be shown as pictorial two-dimensional form. And there are interesting areas in bio and nano areas that newer sensors provide information. And that's I think, not many people working on, so maybe that's an easier task.
Thank you. So the next speaker will be in about 5-7 minutes. Got Hitaker going to talk about space robotics and some of future